Okay, so let's talk about parameter-free sentence embedding via orthogonal bases. So your chatbot, your conversational AI understands sentence embedding. So you can think just like word embedding that you say for each word you have a vector. Now you can generalize that concept and see for a sentence you have a vector. And this paper is a little bit different because it is not parametric. It doesn't require lots of GPU, and it's not like these algorithms. So this paper, also the same authors they have written this paper as well, but this paper is also this extractive summarization. I will explain it in the next lecture, is also important. So the idea is that we want to use Gram-Schmidt process. And it's very important in linear algebra, in control theory, in Hilbert spaces. In everywhere you see the importance of, even in QR decomposition. Even in any kind of decomposition, you will need it. So you project your vector into a subspace. This is the concept of projection. And so you project your U to V, for example, or you could project it into a subspace instead of just a vector. And by using this process, you can create some orthonormal, because they are not only orthogonal to each other, but also they are unit vectors. And so they are unit vectors. So after orthogonalization, you can get an orthonormalizing vectors. As I said, there are two methods for sentence embedding. Parametric method, but non-parametric methods, unfortunately, performance is still bad. But the good thing is that it does not need large-scale training data. And sometimes we call it zero training or zero learning. And it's because like wavelet transform, you don't need to always, for example, in sparse coding, you don't need to learn all parameters. Sometimes a wavelet scattering that, in wavelet scattering, we don't learn anything. It's just what it is. So sometimes we can take advantage of this idea and save time pretty much. And the sentence embedding methods, as I say, we can compare non-parametric with parametric methods. We can see their training time and different measure. For example, for different dimensions, we can compare them. And so when you look at the sentence, for example, a man is dancing. You see, different words have different embedding, but you can think about it as a sentence embedding. For example, a very simple or naive approach to sentence embedding is just, for example, take average of vector of A plus vector of E's. Take average of these vectors, vector of dancing, and what else? Vector of man. If you take average these four vectors, it's a very naive sentence embedding. It's not useful, but it may give you some, for example, at least in what place in space that concept, that sentence that you are talking about is located, so that the chatbot can understand what you are talking about. And so you can, for example, a mathematician likes Grassmann manifold. So each point is in a subspace, and I will tell you how it is related to space of matrices as well. And we can leverage this Gram-Schmidt for QR factorization. So a man is dancing, these vectors can be normalized. They can be, this is an orthonormalized version. So this is the orthonormal space. And the bases are orthonormal Q1, Qt up till Q4. And the columns are orthogonal, and we get a matrix. We don't care. We care about Q, because then we can decompose in this new bases. Of course, it's the same space, but now they are now orthonormal to each other, so that for any word WA we can have a vector embedding for that. And so a space, when I say space S, I mean this space. It is spanned. In control theory, we say span, or in mathematics, we say span of some vectors, vector 1, vector 2. But here it is finite. So it's very simple. So S here, okay. So S is a window matrix. I mean, when you have a sentence, I want to go to get prepared for example, that marathon in Athens. This long sentence, at each word, you can see what are the preceding and followers words. So this get has a vector, and the following. So example 2 is another vector. So you see I've created a matrix that has 3 columns. So this matrix S, which I call it vector 1, vector 2, vector 3. We have 3 columns, for example, with a window of just 1 for this simple example. Our window is just 1. I just need a word and the word after it, or 2 words after it, and 2 words before it. And it is a sliding, so I keep moving. So next time, the next word becomes the center word, and you do the same procedure. So we get the S matrix, and you do it QR factorization. So S is so we define this contextual window matrix, because the name suggests that it's a context. Because if you know a word and the words before and after it, you know what that word in that context means. But after obtaining QR factorization, you can have this nice measure. It says, for example, of course, I don't like it. I prefer something like the inner product, or maybe something else, maybe using the exponential kernel. But here we are using the ratio of them and then taking the exponential. This is one measure to see how important it is to that. For example, here we suggest that word is more important to a sentence if its novel orthogonal basis vector Qi is a large component. And so we can talk about significance of a word to context as well. What is important about SVD is that you can get your diagonal matrix, and more importantly, these eigenvalues. We order them. We say, for example, what are top most important vectors, and those things. So there are 2 ways to decompose using U sigma V, but QR is also another decomposition. So because they are talking about the same vector, I mean SI, it means the matrix that is constructed if you put word I here and then word I plus 1 after that, word I minus 1 before that. And so this is a matrix of 3 columns. So S could be decomposed as a factorization of QR matrix. So this could be a measure of importance of a word to a sentence, to a context, to a text, or anything else. Here, f could be any monotone increasing function like this. F could be anything. Because as long as your eigenvalues, sigma I, it could be any monotone increasing function. And you get top K principal vectors. In this way, you can understand what it means if it is important in the corpus, if it is used in the corpus often. And so this is another score. You get uniqueness score. And so finally, after getting the 3 scores, you add them up, because each one, for example, this takes care of corpus-wide uniqueness score. The other one takes care of some other things, but we need all of them. So we just combine them. Just like in convolutional neural networks, we just aggregate them, aggregate all ideas, all vectors that are in the neighborhood of a node. And so after getting this alpha I, it is just the coefficient of that vector, of that word. And this is our final sentence vector. So as I said, we have a word in a vector. We have a window of size M before that and after that. So we create matrix Si. Then they move it a little bit. For example, now this one becomes center, and we get the words before that and after that, and we create Si plus 1, for example. And so we have lots of matrices. On the linear order of number of words. So it's order of n if you have n words. And so that is the procedure. We have 3 scores, alpha U, alpha S. So this goes, for example, takes care of your corpus, if it is related to the corpus. Alpha S, alpha N, we sum them. If you remember, alpha U plus alpha S plus alpha N. This is the coefficient of that word that I said, like here. And then you are ready to do this is the final sentence embedding. So you see, there is no training, there is no special things that takes big computational complexity, and it's easy. And the algorithm is just a summary of what I said. You get you get S, you get decomposition, you get top K first K singular vectors, and you create alpha I for different scores. Then this is the final sentence embedding. So there are 2 types of infinity. I love infinity. There are 2 types of infinity. It is countable, like countable Markov chain. A Markov chain could have infinite nodes, but it could be countable. Like the basis of for example, in wavelet transform, you have those coefficients could be infinite amount, infinite precision to represent your image or text or anything. But it could be uncountable as well, like Cantor said, I think. And countable is something that I care. And we should care in machine learning because we understand it, we can understand how to control it. We can understand what is the meaning of that. And finally, I want to say about Paul Dirac that All my answers are infinite and I'm scared. I mean, all natural things are infinite. Forget about machine learning, that everything is simple and finite. Machine learning is still in its infancy. They should follow the pure mathematics, and they should follow those French mathematicians that have great ideas.